So the basic Boolean operations that we've talked about so far become way more interesting when we start looking at them as bitwise operators. So to get the most out of this third part, uh, you really need to understand how binary numbers work. Basically, be able to convert from decimal to hexadecimal to binary, because that's where the bits come from. So let's look at these operators as these operations as bitwise operators. So let's start with AND. Let's say we have the the number 3 and the number 5. Okay, now you'll notice for a bitwise operator, there's only one of these ampersands. That's the same for the OR. We can write 3 or 5. We use one pipe to indicate that it's a bitwise operator. Then we have exclusive OR is the little caret sign. So this is 3 exclusive OR 5. And then for the not, if we have a tilde, that is the not. So let's look at what each of these mean. So for the AND, what we need to do is convert these decimal numbers into their binary equivalents. So a 3 is 1, 1, right? And let's just fill this out to 4 binary digits. The 5 is going to be 1, 0, 1, right? The 4's place and the 1's place. Again, we'll fill it out. So if we do the AND of these two numbers, then we look and we do the same kind of truth evaluation, but instead of doing it on the level of 3 and 5, we actually do it on the level of the bits themselves, right? So now a set bit or a 1 bit is true and a 0 bit is false. So if we go through the bits, we look and we say, okay, this 1 bit and this 1 bit, yeah, that's true, right? True and true is true. Now this first bit is true, but the lower bit is false. It's 0 or unset, right? So since one of them is false, it's false with respect to AND. The same is true for this digit here, and in this first binary digit, none of them are set, so none are true, therefore it's false, right? So this 3 and 5 is equal to the number 1. All right? Now, let's look at it for the OR case. Again, we have the binary representation of these numbers. There's the 3 on top, there's the 5, and now we're doing an OR. Okay? So, 1, true or true, right? So both of them are set, which is good enough. That's going to be true. That would be the number 1. Same here. One of them is true. So with OR, true or false is true, right? Because one of them is true. The same for this other digit. And this first digit, neither one of them is true. So we are going to set that to 0. So this equals the number 7, right, in decimal. Now, exclusive OR. This is the really cool one. This is the operation that we use a lot in cryptography, and we use it in a lot of other scenarios too. It's kind of nice. It allows us to easily pick which bits to flip, and you'll notice how this works here. So if we do an exclusive OR of this, start at the ones, at the lowest digit. So true or true, one or one. Sorry, true exclusive or true, or one exclusive or one. This is false, right? There's no exclusivity here. They're both true. Now here, in these two digits, one is true, the other is false. So we do have the or there, and we have the exclusivity. So these next two digits are going to be 1. And then false, exclusive or false, well, that's 0, because neither one of them is true. Okay, so this is 6, right? That's the decimal. Um, this number in binary is 6 in decimal. One interesting thing about XOR is when you XOR one number from another, one of the numbers kind of serves as a mask. You'll notice this lower number, for each of the bits that are set, it flips the bit of the other number. But otherwise, it keeps the digits unchanged. So in this lower number, the 1 is set, the lowest 1 is set, and it flips it from a 0 to a 1. Now, the next number is 0, and it just keeps what it was before in the top number. And for the 1 in the lower number, it again flips a 0 to a 1. And the 0 here, it stays as 0. So it's kind of, XOR is kind of like, can serve as a mask to flip bits all at once. It's kind of a interesting operator. Okay, let's look at not. This is the tilde 5. What we're going to do is reverse all the bits. So when we talk about this not, we need to actually look at how these bits are expressed. So now we have to write all the bits out because they're all going to change, all of them, right? So let's say this 5 is a 32-bit int, which it often is. We write the first 4 bits, 8, and then 12, 16, 20, 24, 28, and now finally 32. Okay, so now if we do not, if we do not on these bits, we simply flip them. Boom, 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 boom. Right? We just change all the zeros to ones, and the ones become zeros. All right, easy. Okay, so these are the basic bitwise operations. Again, they're really good to know. They're also really nice to combine. You'll often see them written together. Um, there is an order of operations that go with them. I won't even mention the order of operations because I think it's a good idea to always use parentheses when you use when you compose bitwise operators. Okay, because the person looking at your code may not remember the order of operations, and they will definitely thank you for using the parentheses. All right. So the next part, the final part of this series, we will talk about the shift operators, which are really awesome to combine with these bitwise operators.